Good morning, everyone. I hope all of you are doing fine and ready to dive into what we were talking about. What is inside this or that, right? And that's how we are going to introduce different junctions to you. So we talked in the previous video about junctions. What are the different kind of junctions in the semiconductor devices or semiconductor world? And this is very interesting because these are the junctions which are defining the real property of whatever we see, right? The function of those devices. So one of the thing which we see, let's talk about what is inside that. So if you've seen typically when you have, let's say, for example, any chip or microcontroller or your Arduino, right? So this is a chip, and there is typically a positive and negative terminal coming out, right? And you apply or a microcontroller. This could be right a whole system where you apply a DC supply and then you power this microcontroller, right? That is the basic idea, and that's how the internal circuits are working. Now the question is, if you don't know where is positive and negative, and you connect, you have a battery, right? And rather than connecting it this way, you connect it the opposite way, right? What would happen? Would your circuit, because now it is going to have something interesting, right? Interesting in the sense that rather than applying the negative where it should be, you have applied it opposite to that. So what is that going to do is can create problems in your circuit, because if there is a current flow which starts to happen in your controller or chip, then I think you are done, right? Because that means that there is something happening which should not happen. There should not be any current which should be drawn. Let's say this is the circuit in which it is going, right? This is just simple example of a load. So you should see when this is the case, whatever you are seeing from this current should be zero, right? There should not be any current drawn if your battery is connected wrongly. So how do you protect that, right? How do you really protect? And that is what we see, what is inside the protection circuitry, right? A protection. How does, or the question is, how does your chip protect against our mistakes or against human mistakes, right? Like connecting the battery opposite to that. And how does it protect? Because it does need some kind of protection. That means it needs some block. So let's say this is the positive terminal. When I'm connecting the battery, so there is a block, let's say like this. So when there is a battery which is connected like this, right? This works fine. That means the current, this is providing a path to the current, right? Because this is correct way it is arranged. But when it is not arranged correctly, right? Which is the case where if you connect it the way like this, where your positive is connected to this, what it should do is it should restrict, right? So there is no current should flow, no current should flow, right? Similarly from here also, no current, right? So then you can already see that what kind of device would we want if we want to restrict the flow of current in one direction and make it flow. And this device we have talked multiple times, which is we know as diode, right? So what you would put inside these blocks is, you can already see with positive, negative, what would you put? Can you guess what would you put in which direction? So this is the positive direction where we want the current to flow. So that means this is going to be in this forward bias mode, right? So that whenever the positive is applied, this is on, right? Similarly here, you can see we would put it in the reverse bias mode, right? So that means this is negative when it is applied, and then you see that there's a current flow which is happening. So these are also known as something as flyback diodes, right? These are flying in some way, but they are protecting your circuitry, right, or your chip. So in the end, you would see that how do one design these diodes. And if you know that a diode, we have studied one way to design diode, and this is what we were talking about in one of the junction last time. What is happening? We looked at that this could be physically designed where we have a N-type silicon and we put P-type silicon pocket inside it, and we put two contacts to this. This becomes my diode, right? So this is, let's say, positive terminal. So this is one way to make diode. But the question is this the most efficient in this case? And that is why we are asking this question, right? And typically what we see in this, because if it can be drawn like this, we saw that there was a junction which was coming when we combined this and this. If you want to see how the junction was coming, check out the last video or the video where we talk about the junctions in semiconductors. So we saw that there is a junction which is coming because of, and there is no hole or electron there. What is there are your depletion charge or the acceptor or donor charge, which cannot move. That is what is inside this semiconductor, right? So now the question is, if this in this semiconductor, that means we also discussed there is some reverse electric field. So that means when you are applying a battery, you see to vanish this depletion region, because if this depletion region is there, right, this junction is there, the hole here will feel a difficulty to go to this side. Similarly, if electron here would feel a difficulty to go to this side because it is experiencing the force in the opposite direction, right? So there is no. So that is what we do with when we apply a positive voltage to this terminal. What we are doing is we are somehow changing that scenario because we are applying an opposite electric field, right? Because if we apply positive to negative, we are applying opposite electric field. This reverse electric field or the junction electric field is the opposing force against which we have to fight. Now, this opposing force happens to be for PN junction. This opposing force comes out to be around, let's say, 0.7 volt if we are designing this, right? At least we have to apply above 0.75 volt to see appreciable current. Let's say appreciable currents, which we are talking somewhere in the milliampere range, right? That is what we are saying, that for that range or that kind of currents, which we use typically in our electronic circuit, we have to go beyond that, right? So now that is a big problem. Why is it a problem? Because I am going to power my microcontroller with a 5-volt battery, right? So I'm going to power it with 5-volt battery, and you are telling me that you will have a drop of 0.7 or whatever across the diode itself, right? So that means in effect, if both diodes are having 0.7 volt, that means I am actually dropping 1.4 volt just there. So that whatever my microcontroller is getting, right? If it is 0.7 volt, what I'm getting between those two terminals is just 5 minus 1.4, right? So that is just your 3.6 volt. That is what you are getting inside the two terminals. So now this does not seem like a good device to even go for because if I am having such a drop. So is there something interesting that you can suggest by which I can reduce this barrier? Still there is a barrier, right? Because otherwise the current will flow, but I still reduce the barrier in a sense that the voltage which I have to apply to turn it on or make the current flow is lesser. What can you suggest? Let's think of again our what junction can pose a smaller barrier. That is what we are asking a question, right? So typically one can think, okay, when you are doping it lesser, you can do, but then there is a problem with the resistance of the currents which you can have. So the point would be that we have to think beyond the PN junction if we want to think of the junction or the lower barrier. And one way to think is we could design this two different things with two different materials. That is one way that we can think. But let's say if we are sticking to silicon, what is the way that we can design this? There's an N silicon which is there. If I dope it P, I know that this is the situation which is going to happen, which gives me larger barrier. Now the question is, how do I make a smaller barrier? So that is where you bring in a very interesting uh, device called, we call it Schottky diode or metal semiconductor diode, right? The device looks like this. Again, if I draw it, this is your metal and this is your N silicon, right? And what happens is, now when you put in this in contact with this, what is going to happen? Is there going to be a flow of electrons? You would say yes. You see, because my metal is having so many electrons, it's like the sea of electrons. It's an ocean of electrons. How can you say there is no electron there in the metal? Ocean. It's an ocean of electrons, right? Means because it's a conductor. So there are a lot of electrons which we see in this wherever our level at which we are, or the water or the electrons are going to flow, right? Similarly, you can see in N silicon, there are electrons. Yes, 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 there are electrons. Obviously, lesser than that. There are also holes, right? Lesser, because if it is N-type silicon, this would be the situation that you have a lot of electrons. So now you can think already, oh, you told me that when there are many electrons, right, this N is much, much larger than this NS or in the metal. So then there is going to be diffusion which should happen, right? So this metal atoms should diffuse to the other side of the silicon, right? That is what should start to happen. And now the question is, when is it happening? When is it not? Right? And because it brings up uh, uh, one more thing with its junction, is that now we have changed the material. Material means this metal and semiconductor, these are two different materials, right? Now you say, okay, why does it matter? Because if these are ocean of electrons I'm connecting to a semiconductor, why does it matter? My electrons should still diffuse, right? So why do you say that these are two different things? Because that is where you have to see, when we were talking about this diffusion here, right? We were talking mainly in the terms of how, what in the semiconductor, when we were having, let's say, either our P type or our N type, right? So this is our P type. So this is P type, meaning, this is the floor 1. This is your floor 0 here, right? This is this we have seen before also, this kind of thing. This is your floor 1 here of this semiconductor, this part, and floor 0, right? And when you connect them, this part connects. And then what you see is, now, because this guy has lot of holes, right? This is P type. This is N. So when this is having lot of holes, while very few electrons, right? Very few. While the other side, you will have more electrons because it's an N type. So you have more electrons and very few holes, right? So then what you see is, in this particular scenario, that hole, because it's going to see, oh, there is lesser holes here, I can go to this side. And the beauty in this is, but it has to still go through a barrier, right? Because why is it a barrier? Because think of it, this is the direction we are drawing electron energy. So the electron potential energy, because all of this we are describing in terms of electron potential energy. That means your electron, which is here at this, it's a, oh, I have to gain potential energy to go to this, right? So there is definitely some barrier you are going to face when you are going there, right? And that is what we saw, this barrier or this junction was arising from, right? That is when these two things are connected, right? These two things are connected, then you see this barrier is going to appear this way. And that is what you see now, the holes, because in the whole potential energy would be in the opposite direction, right? Because it's the opposite charge of electron. So that means now for holes also there is a barrier. So this is what we know as the You can say this is the electron barrier, right? And this is the hole barrier. And why? And this you see in this diagram also. This is the electric field, which is what we were seeing, right? This barrier is posing this internal electric field, which is what is coming from these two, right? Electron barrier and hole barrier. That is what exactly what it means. Now we are in a regime where we are talking about two different materials. That means one material could have, let's say, this is a lot of electrons. But now we have to see that where these electrons are residing, right? And when you are connecting two materials, you have to know where, let's say this is n-type semiconductor, if we are talking about, where are electrons residing inside you, right? Similarly, we are asking here also, where are electrons? Now, typically, if somebody asks you, okay, where is this thing there on earth or something, let's say, where is this town compared to that town? Where is Shimla compared to, let's say, Nainital or Manali, right? All of that we typically define based on something called sea level, right? So there is some level which is like the level where we say there is a 0 meter elevation, right? So that is the reference which we define. Similar to that, in semiconductor world, we also have, though it's upside down, we have something called vacuum level, right? So vacuum level tells me if my electron goes above it, it's out of the material, right? That is what it means. That so now where is the electron which we define based on this vacuum level? So when you say my electrons are here, let's say, so at this floor are my electrons, right? That is what you are defining. So that part, or how distant it is, so this is, let's say, from the sky, or you can take and this is the floor building you are defining, right? So mine is how many floor building is it yours, right? That is the question you're asking. So this floor where the electrons are residing in metal is what we know as the work function of the metal. Work function means the electrons, this needs this energy in electron volt to go out of the material, right? Which is what the photoelectric effect or photoelectric experiment which Einstein had. So this floor is what will give us this thing. Similar to that, we can draw this floor also in your semiconductor, where we can say, okay, you are here. This is your phi s, which is your this floor in semiconductor, right? This is floor in metal. And this all is defined based on the vacuum level, because that is the material property. That is the material property and how far this is defined, right? So now in this case, when you see that, you are going to see, oh, there are a lot of electrons. If this was an n-type, so that means there are a lot of electrons which are there, right? So this floor is what we call so this, let's say this is conduction band we are talking about. So this will be called an affinity of the, or the electron affinity of the semiconductor, right? I think this, we can talk these properties in some other video. For this, let's focus on how does this give a smaller forward drop, or whatever barrier you were talking about, right? That is the main goal for us to understand. And for that, we are now drawing this, because we have to see what is different when we are analyzing this, right? So what you see is, now you are seeing a lot of electrons, because it's an n-type, and this is, anyway, it is just sea of electrons, right? It's a sea which are there and on this floor. So then this sea of electrons, you see, there's going to be an affinity of this electron to go to this side, but there is a barrier, right? This is the barrier which is there. But what is stopping these electrons? Because this is n-type, so they can definitely come to this side. No barrier for them, right? So that is what you are going to see, that rather than this part, so when we connect, let me again draw. When we connect metal and, let's say, n-type silicon, you see, though there are a lot of electrons, but there is a barrier which is coming, right? While here, there are few electrons, but there is no barrier, so they can go. And they will go towards, obviously, with very close to the physical interface, wherever And then this is the part where you will see your positive charge coming in, right? Because these electrons have gone from this part to this part. Right? And that is happening because there is no barrier for these electrons. So they are going into the sea of your metal, right? In your metal. And now what this does is this, again, if you see, there is nothing here. So this is going to put electric field, right, in this direction. So that is, again, you can see that what is it going to do? It is going to stop these electrons from going this way to that way, right? So these electrons, whatever are going from semiconductor to metal, are balanced flow from, is balanced by what you, it's very similar to what we talked in the PN junction. It's balanced by your opposite electric field, right? Your internal null electric field. So now you see a very interesting thing which we see is that there is now no junction on the metal side, because metal has a sea of electrons. There is no dearth of electrons, right? It's not that it has gone negatively charged because the electrons have gone there, right? While your semiconductor does have, because it has your donor atoms which are there to, which are uncovered when you take out the electrons from them. So let's say the phosphorus atoms, they become positively charged when the electron is going there. So now what do you see in this happening is, one of the things which you can clearly see is the barrier seems also less stronger, right? Less stronger than your PN junction, right? And the reason, you can see already we discussed what is happening here. The flow of it was happening from both sides, and the barrier was existing on both sides, right? So that is amplifying that effect. That means the internal electric field is strong, very strong here. So that means barrier is less stronger, means internal electric field is less strong compared to your PN junction, right? So that is what it means, that and that is the reason why you see that the barrier, if I were to make this diode, the barrier which I need to turn it on. So because let's say if I'm going to apply positive voltage, right, a similar way, and negative here. So that means now I'm going to push an opposite electric field, right? So when I apply positive and negative, so you see that I'm going to push a separate. This is your external electric field, right? So this external, or this is your internal electric field. So this external electric field is going to push and make the internal arrangement in the opposite direction, and that is what the barrier which it poses, before which things happen, is around 0.2 to 0.3, very small, or 0.12, even smaller barrier, depending on how do you design or how you find which metal it is, right? Because you see, it all depends on how you are designing your metal and semiconductor barrier, right? There could be a case where, let me just first, so that is what the barrier you will see, that this kind of diode will have, right? So this is what is typically known as also Schottky diode, right? Named after this scientist who discovered this first transistor, right? Schottky. So then typically, yeah, the barrier is this, and then you can get the currents, whatever ranges you are looking at in milliampere or so, right? So now the question you could ask, the opposite question, oh, you are choosing this somehow. You're saying, okay, the electron from the sea level, if I look at, the metal is here, but it could be that the semiconductor could be here, right? Why do you say that this is the case which would exist only, that this electrons here are restricted? If I have a case like this, then, and this is the N-type semiconductor, but here I have C of electrons. Then the things are very opposite, right? Because now my electron can go easily in my semiconductor, right? And that is where you will see there is no barrier, right? And you will see very nicely what is happening here is you have your metal and your semiconductor, but this there is, because there is nothing happening from here, there's nothing, no uncovering of the depletion region happening, or even if it is there, it is just very minute, right? So that means it's negligible, right? This is just, this part is, junction is not there at all, because there is already pushed this electron, which are pushed without the any needed of any need for any voltage across it, right? Because it's just the opposite. And that is why you would see that this junction would be, there is no barrier in this junction, right? Meaning this is what we know as the ohmic junction. Ohmic junction means that if I apply any voltage across it in both direction, I'm going to get a linear current voltage graph, right? So that is what is happening, because now there is no junction, there is no barrier to overcome. But for the design which we talked about here, you would select the materials in this way that you get this 0.2 whatever you need. So this is the material selection you have to do in such a way that you get, but it would be still lesser than PN diode. So that is what you see is typically there, these flyback diode. If you want a lower potential drop, you would use in protection these Schottky diode as one of the options. So keep learning, keep growing, all of you. Thank you, and see you again. Bye bye.